Hi everyone, here's a little bit of vacuum tube amplifier gold for you. This is some information that you're probably not going to find anywhere else. So I'm going to attempt to show you what's actually going on in a vacuum tube by looking through the glass and show you how overcurrent situations affect the actual vacuum tube itself. We're going to look at a whole bunch of different issues with vacuum tubes. Now this 6360 is a really nice tube for doing this because it allows us to peer inside and look down into the grids. Now, this can be done very carefully with 6L6s and 6V6s, 6F6s, and tubes like that as well. And you can check for a whole bunch of different things. You can see if you have grid emission. You can see if the tube is pulling too much current just by the color of the plates, all sorts of different things. You can even spot internal shorts by looking through the glass. Now, here's something interesting that a lot of people don't know. Even the metal tubes, when they were first designed, were made out of glass, so the engineers could look inside and get an idea of a very good safe zone for the internal apparatus. And I'll give you an example of that here quite shortly. So we're going to take a look inside the tube. I have some pretty extreme magnification happening here and a very interesting looking little colored ball there on the screw. If I move my lamp, very interesting. Looks like a little colored ball over there. Anyways, okay, so I'm going to turn the vacuum tube on, and I'm going to let it warm up for just a few moments. You'll see the filaments start to warm up here. So the filaments that you're seeing right at the bottom here inside, they're warming up that cathode pipe that's inside here, and that's the hole in the end of the pipe. You're seeing the light shine out, and now that pipe inside is getting hot, and that has a coating on it, an emissive coating that allows the tube to work properly. So that's all warming up right now so that the tube can effectively emit electrons. Now, if it was just a plain pipe without that coating, it won't emit electrons very well. So they have a special coating on the pipe. And if that coating wears off or basically just gets bad, the tube gets weak. And that's the problem in a lot of vacuum tubes. And drawing a lot of current through a vacuum tube for a very long period of time will make that coating not perform the way it's supposed to perform anymore. Sometimes it breaks off and it'll splatter on the insides of the tube. Sometimes you'll even see it, in basically excessive emission situations, glowing as little chunks on the glass, things like that. This is actually a really, really big topic, and I'm going to try and cover this as much as I can, and this will really help you understand what's happening in the tube and in this build and in your future vacuum tube builds. So I have quite a few amplifier builds planned here. In fact, I've already been planning for the hi-fi version. So what I'm going to do now is, because as I mentioned in the previous video, if I turn the power supplies on the wrong way, it'll destroy the tube. Now this is one of those tubes that's a little finicky, so I'm not really too worried about it. So I'm going to use this one here as an example, and hopefully it doesn't get destroyed. It is finicky. It does have a bald spot, I guess you could say, on the cathode. I think that was a factory defect, so I am just going to use this. I have a bunch of other tubes that show different issues, the same 6360, and I'm going to show you what grid emission is and all this kind of stuff just by looking through the glass. So again, a little bit of vacuum tube gold for you here. Okay, so I'm going to turn on the power supply. Okay, so that's the plate supply, so nothing's happening right now. There's no current being drawn because there's no screen grid. Now, if I grab my little pointer tool here, let's see which one has a nice sharp end on it. This one does. If you look inside the tube and that little coiled wire that you see right there, that is the screen grid. So that grid there is what is going to act as, you could call it somewhat of a booster. When I turn that screen grid on, when I give that screen grid a supply, it is going to make this tube come to life. It really sensitizes the tube, I guess you could say. So a lot of the times in RF sections, varying the output, the RF output of the tube, they actually vary the screen grid voltage. So they use a potentiometer. This is pretty common in transmitters and things like that. So what I'll do is I'll turn on the screen grid supply and keep a close eye on the tube here. I have the voltage down below 100 volts. So now I'm going to bring the screen supply up, and we're going to watch what happens inside the tube here. You see that purple glow? It's starting to work. Now, there are a bunch of different types of purple glows. This purple glow is a healthy purple glow. When you have a glow inside the vacuum tube, I'm just going to turn this down here. You can already see the plate starting to glow red here with that amount of current, and it's very low. So with different types of purple glows, you could say this ultraviolet kind of color, so I'll just give it a quick blast so you can see it here. See that ultraviolet-y kind of color in there? That usually indicates a really strong tube. Now, if you do that and it's a powdered color, so it's almost like a robin's egg color, and it's, I guess you could say it looks like a cloud inside, that means the tube's gassy. So there's two very different types of glows. You'll see a lot of this kind of an ultraviolet glow shining on the glass of the tube. You'll see that on the glass of many power tubes. You'll see that kind of a purpley glow. That is usually an indication of a very strong vacuum tube, and a very good one. You'll notice the ones in your tube tester that test strong usually are the ones that have that glow. Again, not to be confused with a gassy purple glow. I think I have a gassy 6360, so I'm going to show you one of those as well. At least I think I do. I think it was gassy. I have the ones that were troublemakers off to the side. So. Okay, so I'm going to start turning this up, and you're going to start to see particles glow on the glass. The particles that you see glowing on the glass are chunks of broken cathode, the material off the cathode is on the glass here. So if you keep an eye on the glass right here, actually if I turn this light off, it might get just a bit better. I'll give it a quick blast. See the little particles glow down here? And that's parts of the cathode that have gone onto the glass in different parts of the tube. So I'll just turn this back on so we can see what's going on here. So this is the plate of the tube. This is what's hooked up to the audio transformer, this part right here. And when a tube is drawing excessive current, so basically if you have a leaky capacitor, what it does is it changes the bias point of this tube. So it brings the control grid, that's one of the grids that's closer to the cathode. So what we're seeing here is the screen grid. The control grid is one grid under that. So the grids are kind of wound in a circular fashion here, and then the control grid is inside the other grid, not touching it, but just another grid. And if the bias point is wrong, the tube will draw too much current and act somewhat like having too much screen grid voltage. So what I'll do is I'll turn this up, and I'm going to show you one of the effects of a little bit too much current. Now this will run away very quickly, so I have to be careful with my power supply here. I can turn it back down. Now you see that? That glow means that this thing is drawing way too much current right now. So the tube is drawing too much current, and you'll see that in a lot of vacuum tube amplifiers. You'll see this outer plate area. This is the metal plate right here that's closest to the outside of the tube. It'll start to glow red like that. Now if I leave this, it'll run away, and I'll quickly have to shut this down. Now it's running away. So I have to shut that down. Do you see how that glow got really intense inside there? So lots of electrons flowing in there. I'll do that one more time. Bring it to the point of wanting to run away. Now you'll notice that'll happen when the screen or the actual plate itself starts to get really red. I'm bringing this up slow so I can shut it down before it runs away, because if it does, the tube will just spark and flash inside and completely go away. And it's going to run away anytime. There it is. That was the runaway right there. So if I would have left that on within maybe one more second, that tube would have been uncontrollable. I would have shut the screen grid supply down and everything, and the tube would just go away. Okay? So that's what's happening in here. So whenever you see a glowing plate, whenever you see this red color here happening on a plate, we'll see it form in a moment. Now, a lot of tubes in service will run with just a little bit of a red plate like this. And if the tube is nice and strong, it will actually hold that condition. There's actually a saying that 807s don't sound good unless they have a little bit of a red glow on the plate. All right, so they're drawing excessive current. Now, all an 807 is an old 6L6G or 6L6GA with a cap on the top. That's all an 807 is. It's the same tube. So they put a cap on the top so that they could use them in high voltage application. and crank the plate voltage way up. And of course, if you're going to do that, you have to adjust the screen voltage because it's going to draw excessive current with that amount of plate voltage. But that's the reason that they actually put a cap on the top of the tube up here, is because they want to keep the high voltage off the pins in the bottom of the vacuum tube, because if there is high voltage on those pins, there is a tendency with dirt and garbage and just everyday working with any type of an amplifier or in a mobile application, dirt gets on those and then it creates a point where it can arc between the pins and it creates unreliability. So in order to keep the really high voltage and even RF in some cases off the base of the tube, they just put a cap. So instead of having the lead out wire for the plate running to one of the pins, they run it to the top of the tube to make things safer. Very easy way to do things. Makes assembly of the vacuum tube a little bit more difficult, but other than that, it's a very good solution for high voltage. So what I'm going to do is I'm going to swap a tube in here and show you a different problem. Now, if we look inside this tube, if you look right here, you can actually see the two grids out of alignment inside. So you can see it looks like they're in alignment here, a little out of alignment here, out of alignment here. You can see the two grids and so on as you move down. Now, this means that electrons are going to collide with the screen. And when they're colliding with the screen, the actual grid itself is going to run into a condition called grid emission. So the grid itself is going to try to act like its own cathode. And when that happens, really bad things happen inside the tube. So I'll turn on the power supply here. And now the screen supply. And I'm going to turn up the screen supply and watch what happens in this area of the tube here where the grids aren't in alignment when I start making the tube draw current. Look at that. See that grid wire start to glow? I'd say that that is the most out of align one right there. See that grid wire? The actual grid itself is glowing like the cathode when I give it current. See that? That leads to a very bad scenario. Now, I would never want to use this tube even in a very light application because the grids in this tube are so badly out of alignment that this tube would prematurely fail. So this is one of those tubes right out of the box that has problems. And there you have it. That is grid emission. Now, in a really, you can see that. Look at that. It's just taking right off. Plate is really glowing because you can see that it's really drawing heavy current right in this little area here. So this tube would run away in no time. You can see there it goes. It's just about went away. That's a good thing I have my hand on the screen supply. Not that it really matters with this, but it is kind of hard on the audio output transformer. So that is a classic example of grid emission. So one more time, here we go. Again, this purpley blue glow you see is an okay glow. This isn't gassy. And you can see right here, the plate's starting to get nice and hot. It's really starting to work right in that area. And there it goes. You see how the second portion of the grid there, that second wire started to go as well. See that, how quickly that takes off? I just have to touch the screen grid voltage now and it wants to go away. There it is. So electrons colliding in there big time with that grid, and that's definitely what you don't want. You want the electrons to fly freely through the screen grid and the control grid. So the control grid, again, is the one that's closest to the cathode, so the electrons are flying off that cathode, and you want them to go through the gaps. You want them to go through the control grid and through the screen grid and obviously to the plate. Here's an example of a tube with multiple issues. So this tube has very bad grid alignment, so this is going to have grid emission here and over in here. You can see the bad alignment there. And this tube is gassy, and it really starts to take off when it warms up. So what I'll do is I'll turn the screen supply up. You'll see a glow that looks like the healthy glow. Right there. You can see all the particles on the glass glowing away in there too. So I'll just heat the plate up, because right now it's not excessively bad. And that could very easily be confused for the healthy glow in a tube. The healthy glow in a tube that looks like that, the tube won't run away. This one here will run away. So I'm just going to heat the plate up a little bit. Now this is being operated within parameters right now. You can see right there. Now if you look, see that? Kind of a powder glow evenly throughout the entire tube. That is a gassy tube. Right there. It almost looks like you could see the electrons the way that that's happening. So you can see multiple issues. You can see the screen grid glowing there. And up here, it'll start to glow. And you can see that powder blue glow that will very quickly destroy. See how it just kind of pops in? That will very quickly destroy an audio transformer. So I'll just turn that down and let this cool off, because that is going to be a very hot tube. So when you're looking at that glow, you can see how it was very even throughout the inside, the entire inside of the tube, and that's what a gassy tube will look like. Now, some tubes, this will take a while to come on, like this one, and some of them, it's so bad it's immediate. And chances are that's just from impurities inside this tube that may have leached out of the metals in here. And what's happening is when the tube warms up, of course, it's making this effect all that much worse. Now, this compound in the top of the tube, this getter compound that you see right up here, that kind of chrome spot on the top, is designed to absorb impurities throughout the life of the tube. So basically any, I guess you could say, air or atmosphere that is left in the tube after they vacuum it out of this tip right at the top. So right at the top of the tube here is the exhaust tip. So when they're making these tubes and they're going down the line, you have an induction heater with a coil that goes around the tube, and they heat all of the inside of the tube up red hot while they're drawing a vacuum, and that releases a lot of the impurities and they get vacuumed out of the tip. And then after a certain time spec, what they'll do is they'll, let it cool down. So obviously they don't melt the inside of the tube. And then they seal off the top of the tube, and then they'll flash it. And then this is supposed to take care of all the impurities through the rest of, the life of the tube. Now, in a case like this tube here is obviously has an abundance of it in there. Now, when oxygen gets inside the tube, so when this thing draws atmosphere, this will usually go powdery white color. And if you ever see this a powdery white color, don't even try to test it. The tube is 100% bad. And when you see this go to a chocolatey, like a chocolate milk brown color, that means that the tube has been, off-gassing for a very long period of time. It's been under hard service. You often see that chocolatey brown color in very tired tubes in horizontal sections. And you'll also see it in very tired audio tubes, tubes that have been worked very hard throughout their life. Many audio tubes that have had a chrome spot like this that have turned chocolate brown is due to leaky coupling capacitors and or bad bias settings. So there you go. There's a little bit of vacuum tube knowledge for you, looking right through the glass of the tube. Now, as I can find more examples, move this into the center of the shot here. As I can find more examples for you, I will share more examples of, all of these different types of issues. Now what we're going to do is take a look in the bottom of the tube, and we're going to identify all the internal components without a data manual. I'll show you how to do that on a glass tube. So if you have any unknown tubes kicking around and you want to know what is what inside, I'll show you how to do that just by following the leads in the bottom. So usually you use a magnifying glass or whatever, look in the bottom of the tube and follow the internal parts to the lead out pins. Let's identify the internal components of this little 6J6 tube. Grab my pointer here. Pardon the bright blue gloves, that's so I don't get fingerprints on the glass bulb, so that we can see through the glass. So in the center of the tube, we can see the cathode. It's a rectangular pipe, and you can see the emissive coating here on that cathode. That white powdery coating there. We can see we have two grid support rods, these coppery colored looking rods. Two support rods here, and on the other side, two support rods there. We can tell that these are both separate grids inside the tube. Just by looking, we can see that the wires wrap around this plate. So they're not touching the plate, and they're not touching the cathode, but they wrap around and they go over to this side. And it's the same with this side. You can kind of see that bow in the wires there. See if I can get that. And they're just a little bit better. You see that bow in the wires there? So that goes from here over to the other side. So it's going between the plate and the cathode. So that means that we have two separate triodes in one shell with a common cathode. Now, if we had two support rods, one on each side of the rectangle here and only one grid wrapped around, we would know that we would have a single cathode, a common grid to two plates. But since this is wrapped separately on each side, so you can see this wraps around separately here and here, that means that one side of the cathode is acting as a triode this way, and the other flat portion of the cathode is acting as a triode this way. So a very nice little tube for phase inverter service, just because it's two triodes with a common cathode in one 7-pin shell. That worked out very well. Consequently, this tube is designed for VHF use. So lead length and everything in this tube is very important, and they've also used flat pieces of metal right here. They've spot welded to the internal components to keep inductance down, things like that. So this is a very high frequency tube, but works well in audio service. Little 6J6 tube there. So if we look here, we can see at the bottom of the tube, the grid support rods come out here. So again, these are the coppery colored rods. And right around that grid support rod, you can see the mica spacer. So it's a tight little connection between that rod and the mica spacer. When these tubes get microphonic, or any tubes get microphonic, usually what happens is from high vibration atmospheres, these rods elongate the hole in the mica spacer so they become loose. And then either to music or noise, the grid rods will vibrate, and of course the entire grid will vibrate, and it creates a microphonic tube. So keeping the mica spacer tight around the support rod is very important. In a lot of the modern tubes, they've actually added one more mica spacer with little fingers, that tension against the grid rods to keep them tight. So when they're in, an extremely loud guitar amplifier with, say, 2 tens below the amplifier or something like that, it's not going to vibrate the tube, to the point of, it rattling apart inside. So they keep everything nice and tight with these little mica spacers. That's something that they've started doing with the more modern tubes. That's a very, very good idea. Most of the old tubes do not have that little support finger, that little finger that pushes against the internal components. Some of them, they have those support fingers that press against the plate and the cathode and everything. So nice little design feature there. So if we look at the pins, counting this way, this is pin 1. So whenever you look at the bottom of a tube, and get that into focus, this is pin 1, 2, 3, 4, 5, 6, and 7. Okay, so if we look at pin 1, we know that pin 1 attaches directly to one plate. This is one plate here, that gray thing inside the tube, connects directly to pin 1. We would know that this grid here is associated with this plate, so we would turn the tube around, and we would see that pin 6 is the grid associated with pin 1. And same thing for the other one. If we look at the other plate here, so pin 1, pin 2, so now we're looking at pin 2. Pin 2 is the other plate, connects to this right here, right? So if we want to see the grid that's associated with that, we have pin 7, pin 6, and pin 5. So pin 5 is associated with pin 2. If we want to see the filaments, we can see the two lead-in wires, that run, or lead-in pins, run up to this portion right here. And the filaments are spot welded to those lead-in wires, or pins, whatever you want to call them. Right here, and they go right up into the cathode. If we want to locate the cathode, we can turn the tube around, and we can see the cathode right here. It's got a nice big bonding wire that runs right down to this pin right here, and that pin is pin number 7. We just successfully pinned out this tube, I guess you could call it, without any manual or anything. And this can be done with any glass vacuum tube. So if you have an unknown glass vacuum tube, you can follow the internal components to the lead out pins and identify what it is very easily, just like that. So this is just one example. And this is kind of an odd example because this is a dual triode in one shell, because of the two separate grids on each side of a single cathode. That's not really all that incredibly common, right? But I will go over other vacuum tubes and identifying their internals as well. Look at all sorts of other types of vacuum tubes. Very easy to identify. Just that easy. It's a really nice constructed tube, isn't it? They did a really good job putting this one together. In the previous video, I asked the question, why are the two resistors on the plates of the phase inverter different? So why do these both have different values? Well, if you answered the question, to try and keep the outputs the same in amplitude or as close as possible to each other as possible, you're very correct. So this resistance value here on the inverted portion, so this is the inverted output and this is the in phase. So you could say this is out of phase and in phase with the input here. Usually this value here is just a little bit lower to try and keep everything balanced or as close as possible. And the adjustment of this VR will benefit that as well. That's why I put amplitude balance down here on the other schematic. If you're just joining in now, this schematic with all the values on it is an attachment in the previous video. All the values are written on the schematic there. So you can just go to the previous video and right under the video's description is the attachment. Click it and download it and you'll have everything written on this schematic. Now, there are other things that benefit the balance of a phase inverter circuit too. Putting a constant current sink in this area is a very, very important thing to do if you want very, very close balance in the outputs. Now, a lot of people call this a constant current source. It's depending on the way you look at it. I like to call it a constant current sink. And there's lots of reference to this circuit here becoming a constant current sink. So pentodes do that very, very well. I've designed many of these with pentodes, some with even very small UHF pentodes. They kind of look about the size of a 6AL5, kind of a miniature little 7-pin tube. In fact, the picture of the amplifier on my main page on YouTube has that amplifier that I've designed a circuit with a constant current sink, and it works very, very well. It's a very different design. I have 6 SN7s driving outputs in Class B. There's 600 volts across the 6 SN7s. So that's an amplifier and a little, I guess you could say, a circuit that I'll share with everybody here in the future. That amplifier sounds incredible. So it has quite a bit of time into that thing. But anyways, that's the picture on my YouTube main page. That's been there since day one. So how this phase inverter system works, it's really quite simple. So the triode section here, the inverted triode, acts pretty much like just a standard triode. So what happens is when the voltage goes positive on the grid, the tube is going to draw heavy current, and obviously the voltage at this point is going to drop because this is going to get pulled down, right? So as the voltage is dropping here, right, we have the voltage going up here, the voltage going down here. Obviously, we're going to have an inverted phase right here, right? So as this is swinging positive, this is going to be coming down. So we have that inversion. I've explained this before in my phase inverter explanations. Now, of course, as this is happening, here's the trick with this side here. As this is happening, there's current being drawn across this circuit here. So as the current is being drawn across these resistors, this gets further apart. So the grid on this side is going more negative, shutting this side off. If it shuts this side off, the voltage on this side is going to go up. So while this is coming down, the voltage on this side goes up. We have our phase inverter circuit. It's that easy. There's not a whole lot to this. Our feedback point gets fed right in here, and basically we're just looking for some form of a ratio just to give us enough feedback to work in the circuit. In fact, it may not even be desired at all. I've made amplifiers with no feedback and they sound absolutely wonderful. It just depends on what you're into, and of course, this being a guitar amplifier, this is open to anything. So I have worked out the feedback calculations in other videos showing how to work out feedback in an amplifier. I'll do it again with this one here, and I'll try to figure out an optimum point for feedback, and I'll limit it, right? Obviously, as shown before, if we bottom this out, what'll end up happening is this will go into its own oscillation. Just with too much feedback, you get a kind of a bit of an oscillation on the signal there. So we don't want any of that to happen. I'm still designing the power supply for this. And when I get this all put together, and of course when the power supply is all in there and I figure out exactly what I want to do with that power supply, of course I'll share that with you at that point. Once the amplifier is built, we're going to go through this point by point with an oscilloscope, and I'll show you exactly what all the signals are doing on all the different different parts. I'll talk a little bit about the imbalance and how to balance this, and maybe even give a bit of a demonstration, put a VR in one of these lines just to show you how that will change the amplitude at the output here. Even this, again, this is the amplitude balance. Fine-tuning this really brings these right into their optimum area. Now this, balancing this out really is more for a high fidelity type of application. You very easily just pick a fixed resistor here, and this is just a bias resistor for this area here. I found that even operating this with this bridged was absolutely fine. So this is just establishing a very minute amount of bias for this tube. Again, bridging this thing sounded very, very close, and the sine wave looked absolutely fine with this resistor completely shorted. So this is still up in the air. I'm going to do some more experimentation with this circuit, and when I come to some concrete answers about actually having bias or not in sweeping this, I'll share all of that with you, and then I'll go over all of that with you so that you can understand what I understand as well. So that's all in the making, and that's going to be coming very soon. So I hope you enjoyed this video. If you did, you can tap the heart symbol below to let me know, or leave a comment, and I'll see you all very soon. All right, bye for now.